within the project we decided to only change the geometry of this inner liner, as we call it, to make a perfect custom fit. You will see the result later on. How it is working, we scan the rider, and especially important is the position of the head when you're being scanned. So not that the person is looking like this, because then you have a helmet looking that direction. Yes, I'm getting bold, I know. But you need to be in a certain position to be sure that the helmet is fitting right. Then you need to do some trimming and repairing. That's all on the reverse engineering side. We have to align and put in landmarks. And especially important is the landmark you see over here. That's the line between your ears and your eyes, so that the helmet is positioned in the right way. And then we export this geometrical data and some non-geometrical data, like what kind of comfort does the user want, to the knowledge-based system. This is the system to come to a customized helmet. Very simple. Just a few buttons, and then you have a customized helmet. First of all, we need to import the data. This is the head of one of the people of the project. Then automatically, there's a library with two sizes of helmet inside the system. It picks the helmet that's fitting in the best way already. So we know for sure that there's always a helmet. We have small and large ones, which is fit in the almost perfect way. So not that we have a big head with a small helmet, or a very large helmet with a small head, because then we need a lot of strange things to do. Then automatically the head is positioned inside the helmet, and then especially looking, as what I told you, on the line here above the ears and in line with the eyes. Then we create the surface of the head, and then the grey stuff is the morphed part which fits perfectly to your head and which also perfectly fits to the helmet. Then we slice it in 5 different pieces, because it's easier to do on a manufacturing machine to make it in this way. Internally we make a structure so that it's more lightweight, and in the future we also hope to put in some cooling channels. This was the begin situation with the gaps over here, and now in the end we are facing a perfectly fitting helmet. So that's the general idea of having a customized helmet and how such a design system is working. So we put in the know-how of a template of an existing helmet, we put on some specific technology developed in this project, and in the end we have this helmet. This is our favorite. That's why I want to like to show it. Custom fitting seat not for a Ducati rider, but for a disabled child. They really like to play around on such a quad. Me as a person would also like to do that, but I'm a little bit too old for that. But there's a big danger that a child with this disability is going to fall off. So we want to provide bigger rider security, or greater rider security, and also a better feeling of comfort, so that the child is going to play longer with his toy. We use an electrical quad. We put on, as we have been seeing in the presentation of David, the cushion. Then we put the rider on the quad and the cushion, and then we vacuumize the seat. Then we scan with one of the scanning technologies. We scan the seat, and what we are then doing is, again, we use our user interface to come from that scan data to the perfect fitting seat. This was the standard seat, the template, which was originally on the quad. This was what was being scanned. We defined some lines which almost are exactly in line with the lines you see over here. That's all done automatically. And then in the end we end up with a morphed, customized seat. This was the original seat, this is the customized seat. And also you see over here, the yellow-orange one is the original one, and this is the customized one. And you see that the child is much better positioned to the quad line. Then of course it was being mounted. We are using the same engineering data from the original one. You see it over here, it's being mounted, and then it's being tested by the child. And the best picture of the whole project of 9 million euros so far is this one. It's the smile of this kid. It really, when we saw the pictures, we were not there, only our Spanish colleagues were there. The smile on the face and how he was driving around, that makes life even more beautiful than it already is. So that was about automating it. It almost sounds very technologically, but it's also very nice that we can do some nice applications and helping human beings, just like for instance with the jaw and the prosthesis. CAD functionality for graded materials. Maybe you know what graded materials are, maybe you don't know. Some examples from nature. This is a special stone. and what you see is that the material is going from yellow to a little bit of blue. It's all fading into each other. And with a normal CAD system, we cannot describe it. It's the same with bamboo. It's also. And this, when you go to the dentist, ask for your dental element, go to the CGI machine and then mill it off, and then you see that the root of your dental element is like this. So there's also a graded material inside. The first real application of graded materials was in a space plane project for a thermal barrier. You see here different kinds of materials being sprayed on top of each other to withstand a maximum temperature of 2000 Kelvin, and the difference between this part and this part was maximum 1000 Kelvin. And it should be smaller than 1 centimeter. So it must be resistant to these kind of temperatures. And with normal materials that was not possible. That's why they came up with this layer-based spray metal approach, and in this case the first functionally graded material. We cannot represent that in a normal CAD system. We've seen it, it's just a description of the surface or a full solid. So we have to do something about it. We know that we have rapid manufacturing systems coming available to really manufacture the parts, but now we need a proper interface between the idea of functionally graded materials and the manufacturing. Again, this approach is based on voxels. And what we are doing, as I told you before, each voxel is a volumetric pixel. Each voxel is representing a certain property. So a cube full of voxels, some of them can have a property, some of them they don't have a property. And by defining properties in each of those voxels, you can represent any kind of material you like. Of course, there are some limitations on the editing and the storage, etc. But this is, so far we know, the only approach on how to work with it. Within the project, our TNO developed a system for that, and I will show some examples. How it is working, it's just like a candy stick. I think you all know a candy stick. You describe the geometry, and then you describe mathematically that you want to go from sweet to sour, and internally from white to red. This is a strange kind of candy stick, but that's happening. In this way, we can describe such a product in graded materials. This is the shape, and then mathematically we describe it. On the left side we want to have it red, and in this case on the right side we want to have it blue. Then you see the grading from one side to the other side. You see the result from this description of these two elements in this way. But when we want to add from white to green, you see the product will be represented in this way. So here we have a graded representation of a product. And this is then being translated into material properties, and it can go to one of the rapid manufacturing machines. You can also make it a little bit more complicated than only some smoothing in a few directions. You can also make it, like you see over here, from red to blue, but also that you want to do something with the green fully available in here and somewhere in here. When you make the cut through, you see it being represented in this way. And when you look at the 3D model of the functionally graded material, it looks like this. Why on earth do we need this? I showed you this very small space plane one, but also dental elements. When you look at a dental element, it is not purely white or brown, depending on how much you smoke in Amsterdam coffee shops. But it's a kind of layering of different kind of colors. Also, when you look into a dental technician, you see that he or she is putting on different kind of colors to make the perfect coloring of your dental element. So with this kind of technologies, we can represent the perfect coloring of the teeth, and then we can let a rapid manufacturing machine in the future make dental elements. But also, for instance, injection mold. When you have a conformal cooling channel, you want to have very good heat distribution around the channel, but far away from it, less heat distribution or heat guidance. And with this kind of graded materials, you can control the thermal balance in your mold. Okay, we now know with the results of this project that they can be designed. We can output the voxels to a rapid manufacturing machine, and now the first rapid manufacturing machines come to existence who can also manufacture those parts. Within the project, this is the high viscosity inkjet printing, and they really make 3 materials in a graded structure in one part. Of course, it's not a part which we can put in our Formula 1 car or in our mouth, but it's the beginning. And we also started with rapid prototyping with those SLA models, which when you look at it were falling apart, and now we already have selective laser sintering parts being used in Formula 1 machines. So it's coming there, it's going step by step, and this project is also a small step and the full ground